All right, we're back for the fourth video of 1.2. This one is on end behavior models. We're going to see three new vocabulary terms here: the right end behavior model, left end behavior model, and then finally just the general end behavior model, and no new theorems in this section. So we're going to begin with an example. It's in modeling functions for the absolute value of x very large. For numerically large values of x, we can sometimes model the behavior of a complicated function by a simpler one that acts virtually in the same way. But notice again, for numerically large values of x, that's what we're talking about here. In other words, we're talking about infinity and negative infinity. So let's let f of x be a function. F of x is 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6, and g of x is 3x to the fourth. We want to show that although f and g are quite different for numerically small values of x, they are virtually identical for absolute value of x large. So what this means is as x goes toward infinity and as x goes toward negative infinity, absolute value of x large. All right, so let's check out these functions on Desmos and see what we can figure out. Here they are graphed. Let's even make this a little bigger. Here they are graphed. The green graph is f and the purple graph is g. Now, we can see here for small values of x, we can see this is about negative 8 over to 10. These are very, very different functions. However, as x grows large, we can zoom out. As x grows large, look at the right side here. Don't these two curves start to tend to look like one another? And what we can do is change our zoom here a little bit so that on the x-axis, we could go say negative like 100,000 over to the right of 100,000. And actually, that's what I wanted for the y. Let's try negative 20 here. And let's try positive 20 here. And then let's go as low as, say, negative 100,000 all the way up to, how about like 500,000. Okay, so look at that. These two functions look quite a lot like each other as we go further and further to the right. That is interesting. There we are again, back in very small values of x, but we were able to show that to the far right and far left, these two functions looked essentially identical. And what we can do is prove that mathematically by looking at a ratio of these two functions. Let's do that with limits. So what is the limit as x goes toward either positive or negative infinity of f of x over g of x? Well, that is the equivalent then of the limit as x goes to positive or negative infinity of 3x to the fourth minus 2x cubed plus 3x squared minus 5x plus 6. This is all over just the function 3x to the fourth. Now, this can be simplified quite a bit because when dividing by a monomial, we know that it's actually each individual term of the polynomial in the numerator that gets divided by the monomial in the denominator. So this is equivalent to, again, the limit as x goes to plus or minus infinity, but 3x to the fourth over 3x to the fourth is 1. And then 2x to the third over 3x to the fourth simplifies to 2 over 3x. And then 3x squared over 3x to the fourth simplifies to 1 over x squared. And then 5x over 3x to the fourth simplifies to minus 5 over 3x cubed. And finally, 6 over 3x to the fourth simplifies to 2 over x to the fourth. And if we use the sum rule for limits, the limit as x goes to infinity of 1 is 1, but the limit as x goes to infinity of each of the following terms turns out to be 0 for the same reason that the limit as x goes to infinity of 1 over x is 0. So we get 1 plus 0 plus another 0 plus another 0 plus another 0, and it's 1. And as it turns out then, if we're looking at the limit as x goes to positive or negative infinity of some f over some g, if that's equal to 1, then g turns out to be an end behavior model. And that's what we see on the next page. So here's a definition. The function g is a right end behavior model for f if and only if the limit as x goes to positive infinity of the ratio of the two functions f over g is equal to 1. It's a left end behavior model for f if and only if the limit as x goes to negative infinity of f over g is equal to 1 as well. And if one function provides both a left and a right end behavior model, then it's simply called just an end behavior model. So for instance, in the last example, because 3x to the fourth was an end behavior model on both the left and right side of f, then it's just called an end behavior model. And in general, the leading term of a polynomial is an end behavior model for the whole polynomial function. That's why 3x to the fourth was picked for g when looking at f, because 3x to the fourth is the leading term. It's the term with the highest degree. Okay, so here's an example. Let's find the end behavior model for the function f of x equals 2x to the fifth plus x to the fourth minus x squared plus 1 over 3x squared minus 5x plus 7. So here's what I want to do. The polynomial on top in the numerator, the leading term is 2x to the fifth. So 2x to the fifth is the end behavior model for the top polynomial. And 3x squared is the end behavior model for the bottom polynomial. So my end behavior model is, I'll use h here, is going to be 2x to the fifth over 3x squared, and that's going to reduce then to 2/3 x cubed. So that tells me then, as x grows large or very increasingly small, this function f tends toward the same way as 2/3 x cubed. So a much, much simpler function will behave in basically the same way as this extremely complicated function. Over here on g, here's the leading term, here's the leading term. So we'll use h again. That means our end behavior model, 2x cubed over 5x cubed, that's going to reduce to just 2/5. So that tells me as x grows large, then f of x tends towards 2/5. And we want to note here, because what we see on part B is we are tending toward a constant, then y equals 2/5 is a horizontal asymptote of the function in B, or it might make more sense to say is the horizontal asymptote of g of x. Was there a horizontal asymptote on f of x? There was not, because if we go towards infinity here, this is going to continue to grow without bound. It's because we got a constant value here that we see a horizontal asymptote. So one more example, let's find end behavior models. This one is going to show us that we don't necessarily always see the same end behavior model on both the left and right side. So we're going to show that g of x is a right end behavior model for f, and we're going to show that e to the negative x is a left end behavior model for x. And I have these graphs in Desmos, so let's hide those. Let's look at the original. So this is x plus e to the negative x. We do see some kind of different sort of behavior to the left as we do to the right. You can zoom out a little bit more here, kind of like a big giant check mark or like a Verizon sign maybe. So let's take a look at y equals x. And even though these are very, very different to the left, look at to the right. These are behaving in basically the same exact way. Okay, what about e to the negative x? So very, very different to the right. So as x went to infinity, very different functions. But as x goes towards negative infinity, as we move left, look at that, essentially the same behavior. So we showed it by graph. Let's take a look then at how we would show this by algebra or analytically. So what we would want to do is take a ratio again. So the limit as x goes toward, let's do the right in behavior model first. So as towards infinity of x plus e to the negative x all over x. And we need to show that this limit is 1, right? Because if it's equal to 1, then this is indeed a right-end behavior model. So this limit is equivalent to x over x, so that's 1, plus e to the negative x over x. So then I would simplify one more time that this is the same as the limit as x goes to infinity of 1 plus 1 over x e to the x. And since the limit as x goes to infinity of 1 over x e to the x is 0, here we have 1, and we got it. That's an end behavior model. For the other one, the limit as x goes towards infinity of, here's f, so e to the negative x over, we want to show the left end, so we're using e to the negative x there. And this would be equivalent to the limit as x goes towards, we're doing negative infinity of x over e to the negative x. And then this would be plus 1. What are we looking at here? Well, this limit as x goes toward negative infinity, as x goes towards negative infinity, this goes to 0. So here we have 0 plus 1. So we get 1 again, and there is our end behavior model. Good deal. I'll see you in the last video.